Hi, I'm Jeong from KAIST, and I'm very happy to share our work, FLUID-IoT, a mobile system that enables flexible and granular access control in shared IoT environment using UI-level control distribution. The smart home IoT market is continuously growing. In the worldwide smart home market, the United States continues to lead the way with innovative technologies and widespread adoption. According to forecast, this market is expected to continue experiencing sustained growth. Numerous devices are being integrated into home, workspace, and various other multi-user domains. Accordingly, IoT platforms such as Google Home and Samsung SmartThings have developed features that enable users to invite others to access and manage their IoT devices. However, existing IoT platforms often fall short by offering an all-or-nothing approach to access control, not only posing security risk but also inhibiting the growth of the shared IoT ecosystem. For example, Google Home and Samsung SmartThings allow users invited to the shared IoT environment to control all connected devices without any oversight. An invitation to a Google Home setup grants guests control over all connected devices, even allowing them to view logs and change settings. Many related studies have been conducted. Some studies have introduced and examined various access control policies in shared IoT environment. Moreover, there have been efforts to directly implement these access control policies into IoT applications. In addition, some researchers have ventured into designing a new IoT stack. These endeavors collectively underline the complexity and the pressing need for innovative solutions in managing access within the IoT ecosystem, especially in shared IoT environment. However, modifying the existing conventional IoT stack to introduce access control policies requires a huge technical effort. This is our research question: how to integrate access control policies into existing IoT platform seamlessly and easily. Our high-level insight is that since IoT devices are typically controlled through graphical user interface as an intermediary, by regulating access to this interface, we can effectively control access to the devices themselves. If a user cannot access the control interface, they cannot control the device. Our research goal is to design and implement to seamlessly integrate flexible and fine-grained multi-user access control to existing IoT platforms. To achieve this, we employ a UI distribution technique that retrofits existing IoT platforms with function-level access control. For that, we utilized FLUID-XP technology. In 2021, our research team published a paper, FLUID-XP, at Mobicom. The FLUID-XP technology is based on the Android OS framework, enabling multi-devices interaction within a custom operating system. In this scenario, we can see the capability of FLUID-XP technology by taking the chat UI component of the Twitch app, which typically runs on a single device and seamlessly transferring it to another device. We have expanded the multi-device paradigm of FLUID-XP to encompass a multi-user framework, applying this technology to access control. Our concept is straightforward: selectively distribute IoT control UI component from a single device running an IoT app based on each user's permission. As a result, users are only able to interact with the UI components that have been shared with them. In a practical scenario, you can see that while Alice and Bob may receive some control permissions, Jeong would have no authority over the verb and only partial permission for the speaker. The FLUID-IoT system operates as follows. The host device communicates with IoT devices through an existing IoT platform like Google Home. The Fluid Host framework is comprised of three main components: the UI extractor, UI renderer, and the UI streamer. The UI extractor is responsible for extracting the IoT control UI from the IoT platform app. Following this, the UI renderer takes over the extracted UI component. Finally, the UI streamer distributes the rendered UI to guest devices. However, our project encountered two primary technical challenges. First, how to make UIs across different activities to be accessible and distributable for simultaneous multi-user interaction. Second, how to distribute UI selectively to multiple users while maintaining a responsive and consistent UI interaction. In multi-user IoT environment, different users often want to control different devices. However, the control UIs for different devices are usually scattered across various activities within the IoT app, requiring constant switch between activities to, at best, sequentially handle each user interaction. To tackle this issue, we employ a multi-activity execution technique. Usually, Android OS runs on a single activity model, meaning it does not allow for simultaneous access to multiple activities. To navigate between activities, users typically must press the back button to move to another activity. The FLUID-IoT system is designed to distribute the UI of the single host device. However, in a multi-user environment, we need a solution that allows users to simultaneously access UI in various activities. To address this challenge, we enable the IoT app to run multiple activities on the foreground. To extend such design, we leverage Android OS's launch objective feature. This feature enables app to launch multiple activities side by side on the same screen, which is originally intended for developing a multi-window app targeted for large screen or multi-screen devices. As a result, the host app can seamlessly handle actions from multiple users accessing multiple activities simultaneously. Another important consideration is maintaining responsive and consistent UI interaction across all user devices. This is especially critical in the IoT landscape, where unsynchronized UIs may lead to unintended user action due to misinterpretation of device state. For instance, a delay in updating the light bulb status could lead a user to repeatedly pressing the power button, inadvertently turning off a bulb another user had already switched on. To address this challenge, we introduce dynamic UI channel switching, a method that uses multiple multicast channels to reduce synchronized lag. UI Streamer dynamically switches the UI streaming channel based on which UI should be displayed on which user devices. UI Streamer streams only the UIs that are authorized to the user's device. This allows each user's device to have a different set of UIs displayed on the FLUID user app, and to be able to swap between control activities, as though it is running a real IoT app. This design choice makes implementing access control in FLUID-IoT remarkably straightforward. We selected 3 access control mechanisms for implementation: different access control, time-based access control, and supervisory access control.
FLUID-IoT allows users to grant different levels of access to different users with granularity down to the UI level. Let's first give the user a full control over the smart speaker. You can select which UI is permitted to which user simply by clicking on the UIs. But for user B, let's allow her to control only the volume, but nothing else. You can also give temporary or time-based permission. Let's allow user A to use the bulb only from 4 p.m. to 5 p.m. Just click on the UI you want to give temporary permission and set the time period. At the time period, the bulb UI will automatically disappear from the user's screen and she will no longer be able to access the bulb. You can also give supervisory permission to monitor other users' actions over the IoT device. Let's set user B to supervise users' actions on the smart bulb. You can specify the supervision relationship between the users. Click on the UIs you want to be supervised and set user B as user A's supervisor. Now, whenever user A tries to control the speaker, user B gets notified. User B can choose to either approve or revoke user A's action.
We conducted a usability study based on these implementations involving 17 participants. Our key findings are as follows. Participants acknowledged the significant usefulness of advanced access control in a shared IoT environment, and the conversion of system usability scale to an objective rating scale resulted in an excellent score, confirming its usefulness. Interestingly, the feature that displays only the permitted UI element to user was found to be highly beneficial, not just for administrators, but also for users themselves. In terms of performance and resource consumption, FLUID-IoT showed efficiency. When managing the UIs of 3 different IoT devices, the system requires only an additional 17.83 MB of memory. This is less than 0.3% of the total memory capacity of modern smartphones, which typically have around 6 GB. And the system's responsiveness feels instant to users, significantly enhancing the user experience in multi-user settings. This improvement is largely due to the notable lower synchronization latency FLUID-IoT achieved. We tested the top 8 IoT apps from the Google Play Store. Our tests showed that FLUID-IoT works effectively with most of these apps. This is conclusion. We have designed and implemented FLUID-IoT. By selectively distributing control UIs to users based on access control policies, FLUID-IoT effectively manages access to IoT devices, ensuring a more secure and efficient environment. Our evaluation of FLUID-IoT highlights its effectiveness in terms of performance, coverage, and usability, affirming its role as a significant advancement toward a more capable and safer IoT ecosystem. Thank you for listening.